I've been trying to colour these hexagonal pyramids so that they all look different. I'm not attempting anything fancy. I'm using just the two colours of paint, purple and yellow, and only one colour on each face. My question is, how many different pyramids am I going to end up with? Now, at first glance, this must seem to be a rather simple problem. I'm ignoring the base, and so I've just got the 6 visible faces of the pyramid to worry about. Now, I've got 2 choices for each face, so apparently that's 2 to the power 6, in other words, 64 possible colourings. But just look now at this pyramid. It may look rather different from the first one, but you see, when I rotate it like that, you can't tell them apart. And so I can only count this as one colouring. And similarly, these 3 pyramids also look a bit different, but again, after rotation, you can't tell one from the other. So again, this is only one colouring. And similarly, these 6 pyramids are also essentially coloured the same. If you start with that one, I can rotate each of the others in turn so that it looks exactly like it. Now, of course, when I come to look at this all-purple pyramid, no matter how I rotate it, it just finishes up looking exactly like itself. In fact, it's in a class all of its own. And obviously the same is true of this all-yellow pyramid. Now, these are only some of the essentially different colourings of the pyramid. And the problem is, how many are there altogether? Well, we could go on to look at all the 64 possible colourings, and we could identify the essentially different ones. But that sounds a bit too much like hard work. Surely there must be a more intelligent way of doing it. And that's really the question. Can mathematics be applied to the solution of problems such as this? Well, indeed it can. As we shall see, group theory gives you quite an elegant solution of a whole class of problems of this type. And using groups, you'll be able not only to count the number of different colourings, but even to list them all.
The only group in evidence is made up of the various rotations we've already mentioned. In other words, it's the group of direct symmetries of the pyramid. And when you consider how this group affects the set of all 64 possible colourings of the pyramid, what you get is an example of a group action. The group of symmetries acts on the set of colourings. It rotates certain colourings to look like others. I'm going to illustrate the group action with this model. It has the set of pyramid colourings at the back and the group of symmetries at the front. The elements of the symmetry group are all rotations. I've colour-coded them, which will help us later on. For example, this rotation is coloured purple. It rotates each face clockwise through one face position. There are 4 other rotations, each of which rotates the faces through a different number of positions. And you mustn't forget the identity, which doesn't rotate the pyramid at all. So altogether, there are 6 elements in the symmetry group. Now, what are the elements in the set of colourings at the back? Remember, this is the set of all possible colourings of the pyramid. So there are 64 elements in all. But I've drawn in only some of these colourings, the ones we've already identified. And I've arranged the colourings into layers, so that essentially different colourings are in different layers. Let's start by looking at the colourings in just one of the layers. For example, this colouring with 5 purple faces and 1 yellow one. What's its relationship to the other colourings in the layer? Well, watch what happens if you let each symmetry act on it in turn. That gives you all the other colourings in the layer. This set is called the orbit of the colouring. What about this colouring? What happens when you let each symmetry act on it in turn? Stop the tape and work out its orbit. You should have found that the orbit of this colouring is again exactly the set of colourings in its layer. And the same thing happens for every other colouring. Each layer in the model contains just the colourings in one orbit, and each orbit consists of colourings which are essentially the same. Remember, our problem is to count the essentially different colourings of the pyramid, and now you know that's the same as counting the number of different orbits under the group action. But that doesn't help much unless you can work out how to count the orbits. To find out how to do that, we'll need to investigate the relationship between the symmetries and the colourings in more detail. We already know that some symmetries change one particular colouring into another. For example, consider this colouring. The rotation through two face positions does affect this colouring. It looks different after rotation. But the rotation through three face positions doesn't affect the colouring. It leaves it looking exactly the same. To indicate this, I'll draw a connection between the colouring and the symmetry. I've colour-coded the connection according to the symmetry. In the same way, I'll draw a connection to each symmetry which doesn't change the colouring after the rotation. In fact, the only other symmetry that doesn't affect this colouring is the identity. I'll draw a red connection to indicate this. What I've done is select the set of all symmetries that don't affect the colouring. This set is called the stabiliser of the colouring. What about this colouring? Which symmetries don't affect it? Stop the tape and work out its stabiliser. You should have found that the stabiliser of this colouring contains three symmetries: the identity, and the rotations through two faces anti-clockwise, and through two faces clockwise. In fact, both the colourings in this orbit have three symmetries in their stabiliser. One of the colourings in this orbit has two symmetries in its stabiliser, as you've seen, and in fact, the other two colourings have the same stabiliser. In this orbit, however, the colourings have only one symmetry in their stabiliser, the identity. And there's only a single colouring in this orbit, but it's unaffected by any symmetry, so it has all six symmetries in its stabiliser. And the same is true for the all-purple colouring. Can you see a pattern emerging? There are the same number of connections from each orbit. In each case, the size of the orbit times the size of the stabiliser is the same. In fact, it's equal to 6, the order of the symmetry group. This is an important theoretical result called the orbit stabiliser theorem, and it's proved in the unit. But how does this help count the orbits? Well, the number of connections from each orbit is equal to the order of the group. So if you count all the connections in the model, then the grand total will be the order of the group times the number of orbits. Putting this another way, you can say that the number of orbits is given by the total number of connections divided by the order of the group.
So that very nearly allows you to solve the problem. You know that different colourings correspond to different orbits, and now you have an expression for the number of orbits. The trouble is, we've only looked at some of the possible colourings of the pyramid. Of course, in this case, you could look at all the 64 possible colourings. That's a bit tedious, but is still quite manageable. However, you will encounter problems where the number of colourings is prohibitively large, even if only because more than two colours are in use. So what do you do then? Well, let's see what we can do by looking at the other end of the connections, where we only have to deal with the 6 elements in the symmetry group. For example, what about this symmetry that rotates through 2 face positions? It has 4 blue connections from it. They're connected to the set of 4 colorings that are unaffected by this symmetry. And this set is called the fixed set of the symmetry. But how can you work out this set of colorings? To get a better idea of what happens to the pyramid after a rotation, let's number the faces. And now let's consider how the faces are permuted by this symmetry. First, what happens to the odd-numbered faces when I perform the rotation? The faces move round in a cycle. Face 1 moves to position 3, face 3 moves on to position 5, and 5 moves round to 1 to complete the cycle. So that gives a cycle 1, 3, 5. Similarly, the even-numbered faces move round in another cycle. Face 2 moves to position 4, face 4 moves on to 6, and 6 moves round to 2. So that gives the cycle 2, 4, 6. So this particular symmetry is the product of 2 disjoint cycles, 1, 3, 5, and 2, 4, 6. But how does this help you to find the colorings of the pyramid that are unaffected by this symmetry? Well, if face 1 is colored purple, then face 3 must also be purple, and similarly face 5. All 3 faces in the cycle must be the same color, all purple or all yellow. That's just 2 choices of color. And now, if you choose the color for face 2, then face 4 must be the same color, and so must face 6. So the faces in this cycle must also all be one color, all purple or all yellow. And that's another 2 choices. But the cycles are disjoint, which means you can color them independently. And so the number of possible colorings of the whole pyramid that are unaffected by this particular symmetry is 2 squared. You can see this on the model. The symmetry is connected to precisely 4 colorings. What about the rotation through 3 faces? How many colorings does it leave unaffected? Well, stop the tape and work out its psychorepresentation for yourself. Then use it to calculate the fixed set. What you should have found is that the rotation through 3 faces can be represented by 3 disjoint cycles, 1, 4, 2, 5, and 3, 6. The faces in each cycle must be the same color, but each disjoint cycle can be colored independently, with a choice of 2 colors for each cycle. And so there are 2 cubed colorings that aren't affected by this symmetry. But remember, for the previous symmetry, we found the size of the fixed set was 2 squared. What do you notice about the power to which 2 is raised in each case? Well, the power of 2 is always equal to the number of disjoint cycles in the symmetry. So you can work out the sizes of the fixed sets for the other symmetries just by looking at their cycle representations. Rotation by one face anti-clockwise produces 1/6 cycle. And so we get 2 to the power 1, or just 2. And the rotation by one face clockwise gives the same answer. We've already seen that the anti-clockwise rotation by 2 faces gives 2 squared, and the rotation by 2 faces clockwise gives 2 squared as well. Finally, the identity leaves each face fixed. The identity is really 6 1 cycles. And so that gives a fixed set with 2 to the power 6 colorings.
Now you have all the information you need to work out the number of different colourings of the pyramid. Remember, what you actually want to find is the number of orbits. And to do that, you first need to find the total number of connections by summing the sizes of the fixed sets. Then you divide by the order of the group. In other words, you average the sizes of the fixed sets over all the symmetries in the group. And when you do that, you find a total of 84 connections. That means just 14 essentially different colourings of the pyramid. Stop the tape and check this out for yourself.
Well, that's solved our particular colouring problem. But we've had to build up quite a bit of mathematical machinery to do it. However, we shall find we can make good use of it, because the same machinery will give us the answer to more than just this one problem. For a start, suppose we increase the number of colours. Let's say we have m colours available, and for the moment we won't commit ourselves as to what the value of m is. Well, the remarkable thing is that most of the work we've done carries over immediately to the new problem, because once again we can find the number of orbits simply by averaging the sizes of the fixed sets over all the symmetries in the group. So what we have to do is to work out for each symmetry what its fixed set will be when m colours are available. Let's look again at the rotation which moves everything through two face positions. As before, if we choose a colour for face 1, then face 3 must be the same colour, and so must face 5. This time, however, there are m colours available. So how many choices are there for these three faces altogether? Well, there are m choices, and similarly, faces 2, 4 and 6 must be the same colour, and so there are another m choices for these three faces. And these two choices are still independent, just as they were before. So the number of possible colourings of the whole pyramid that are unaffected by this symmetry is m squared, where before it was just 2 squared. What about the symmetry which moves through three face positions? Stop the tape and work out the size of its fixed set when m colours are available. You should have found that the fixed set now contains m cubed colourings. In fact, where before we had 2 raised to a certain power, we now have m raised to the same power. This power is the number of cycles in the symmetry. The same thing happens for all the other symmetries in the group. And now we can work out the number of orbits for m colours. We add up the sizes of the fixed sets for each symmetry and then divide by the order of the group. If we put m equal to 2, we should get the same answer as before. And indeed we do. We get the 14 essentially different colourings. But now you can put any value of m you like into this formula. Putting m equal to 3 gives 130 essentially different colourings with 3 colours. Putting m equal to 4 gives 700 different colourings with 4 colours. So now perhaps you can see why earlier on I wanted to avoid examining all the possible colourings.
So now we're really getting something back for our efforts, but the machinery can be developed to do even more than this. We can actually use it to list all the essentially different colourings in one fell swoop. So far, we've only considered the number of disjoint cycles, but we have some more information at our disposal, the length of each cycle. Let's go back to the symmetry, which rotates anti-clockwise through 2 face positions. With 2 colours available, faces 1, 3 and 5 can be purple and purple and purple, or they can be yellow and yellow and yellow. And faces 2, 4 and 6 can be purple and purple and purple, or they can be yellow and yellow and yellow. We can summarize this information in a polynomial. It's called the pattern inventory, and its terms list all the colorings in the fixed set of this symmetry. If you haven't already done so, read the video notes which explain how to obtain this pattern inventory. You should have found this pattern inventory for the colorings that are unaffected by the rotation through two face positions. To list these colorings, all you have to do is to multiply the inventory out and consider the terms one by one. The first term tells you that there's just one coloring with 6 purple faces. The second term tells you that there are 2 colorings with 3 purple faces and 3 yellow ones. So what are these colorings? Well, there's one colouring with odd faces yellow and even faces purple, and one with them the other way round. And the last term tells you that there's one colouring with 6 yellow faces. Before we go on, let's check that this is right by looking at the model. Here's the symmetry, and there are 4 blue connections from it. One to the all-purple pyramid, one to each colouring with the 3 purple faces and 3 yellow ones, and one to the all-yellow pyramid. So the pattern inventory has given us an exact list of the 4 colourings which are fixed by this symmetry. And you can work out the pattern inventories for all the other symmetries in the same way. And now you can use this to get a complete list of all the different colourings of the pyramid. You simply add up the inventories for each symmetry and then divide by the order of the group. Multiplying out gives this polynomial. So let's interpret it as an inventory term by term. There's just one colouring with all 6 faces purple, and one with 5 purple faces and 1 yellow. But there are 3 colourings with 4 purple faces and 2 yellow. So what are these colourings? Well, there's one with 2 yellow faces adjacent, one with the 2 yellow faces 1 face apart, and one with them 2 faces apart. And if you carry on like this, you get a complete list of the 14 different colourings of the pyramid. Stop the tape and check these 14 colourings really are the essentially different colourings of the pyramid. But what happens if you want to generalise this listing to M colours? To do this, you really need to automate the process of producing the pattern inventory. This is where the device known as the cycle index comes in. The cycle index of a permutation is simply a symbol recording the length of each cycle. For example, look at the identity. It has cycles of length 1. We'll use the symbol x1 to represent each of the cycles, with the subscript 1 recording the cycle length. Just as with the pattern inventory, we'll multiply the symbols for the different cycles within each symmetry. The identity has 6 1 cycles, so its cycle index is x1 raised to the power 6. And you can construct the cycle index for each of the other symmetries in the same way. The anti-clockwise rotation by one face has a single 6 cycle, giving just x6. And the clockwise rotation by one face is the same. The anti-clockwise rotation by 2 faces gives x3 squared, corresponding to 2 3 cycles. And the clockwise rotation by 2 faces is the same. Finally, the rotation by 3 faces gives x2 cubed, corresponding to 3 2 cycles. Now you add up the expressions for each symmetry and divide by the order of the group. And then you can feed in the symbols for however many colours you have available. If you're colouring the pyramid with two colours, purple and yellow, you take x1 in the cycle index and replace it by the inventory symbol for purple or yellow. Take x2 and replace it by the symbol for two purples or two yellows. And you carry on in the same way all the way up to replacing x6 by 6 purples or 6 yellows. That gives the same inventory for the two colours as we had before.
But now suppose you had three colours. Let's say red, green and blue. In this case, you would replace x1 by the symbol for red or green or blue. And you replace x2 by the symbol for two reds or two greens or two blues, and so on. In this way, you build up quite a large polynomial, which you could expand to give you a complete listing of all the 130 essentially different colourings of the pyramid using three colours. But if all you want is the answer to a more specific question, you won't need to do all that. For example, take a look at this pyramid. Suppose you want to find how many different pyramids like this one have got two red faces, two green faces, and two blue faces. Well, I'm going to leave you to tackle that problem for yourself. After you've stopped the tape, you'll find the details in the video notes.